Hello, I'm Lavanya, and I'm a postdoc based at U of A in Tucson, Arizona. Today I'm just going to be talking about my current research, which is the modeled mass loss rates from Arctic glaciers using a combination of remote sensing and modeling techniques. So before I begin talking about my research, I thought I would give a background about my research and my expertise. So I'm basically a remote sensing. I'm into remote sensing. I did my PhD from Swansea Uni with Adrian and Bernd as my supervisors. So during my PhD, I was interested in looking at glacier velocities from glaciers in Himalayas over a longer temporal period and high spatial resolution. And also I'm interested in knowing what sort of relationship exists between dynamics and climate. So in my postdoc, I'm trying to understand what's the mass loss rates using modeling techniques, which pretty much forms my background. And then my current research has been understanding how these modeling techniques, how we can better use remote sensing, especially in modeling techniques, and to understand what's the present and future mass loss rate. And I'm also interested in using these climate ensemble models from CIMIF 5 and CIMIF 6. So other than my research, as Lauren mentioned, I'm into the SEM and outreach activities, being a outreach member with AWG at UFA and also US APEX. So I'm happy to talk to anyone who's interested in early career initiatives. So coming back to my research, I would like to know what I'm sort of interested in how these mass loss rates are, and what are the processes that are affecting these mass loss rates, particularly from glaciers. And we know that glaciers have been losing a lot of ice, especially in terms of sea level rise, compared to the ice sheets that we have. And I'm interested in how we can use these remote sensing techniques to understand these processes much better. Particularly interested about Arctic glaciers. So a bit of background about these Arctic glaciers. And we know this is one of the original glacier contribution to sea level rise from Zemp's paper, where we have all these glaciers, the RGI glaciers across the globe, and out of which, when we see these Arctic glaciers, we find the Gulf of Alaska North, Gulf of Alaska and Canadian Archipelago are the largest contributors to sea level rise. And also with the current rate of warming that we have, it is expected that these glaciers could be losing a much larger rates in the coming decades. So in the next few decades. So it's important how we understand these glaciers, especially the Arctic glaciers, using these modeling studies. So the model that I use is based out of temperature index method. And I would like to acknowledge the amazing models that are out there in the Glacier MIP, which is Glacier Model Intercomparison Project. So our idea is based out of these temperature index method, where we use temperature and precipitation in our model to calculate the ablation and accumulation. So one of the inputs that goes into ablation, the input that goes into the ablation is temperature, which we calculate at elevation bins. And for accumulation, we use precipitation, and which is also at elevation bins. And on the right here is history of glaciers in Alaska, which is based on the RGI 6.0. And when we calculate this ablation, we have other parameters such as, say, degree day factors. And then in calculation of accumulation, we have parameters such as precipitation gradient, which is the precipitation change over these elevation bins, and also the correction factor, and also the lapse rate at the ERA, or the lapse rate at which use it for precipitation. I will talk about these model parameters later in the next coming slides. And then I wanted to introduce you to gray space mass balance that we're trying to use here. So we have GRACE observations. So I use GRACE observation from RLO6 CSR between 2002 and 2016, from which we have 160 monthly observation. And the technique that we use to attain these mass loss rates is by using Selepian functions. So Selepian functions is one of the ways in which you can transform, or in which we can recover these mass loss signals from the spherical harmonics which is available in the geodesy. And then one of the important, I'm not going in depth into these mathematical formula, but just happy to answer any question that you have with Selepian functions, which you can ask me later. And then these are known to like maximize the energy for a specific region. So as you can see, like we always have this problem of leakage, which happens in these Arctic regions. If you take Baffin and Ellesmere, we have a lot of signal leakage that's coming from the large polar ice sheets, namely Greenland. So Selepian functions have been like able to recover mass from a predefined region, as you can see. We use these RGI. RGI outlines to do these user-defined regions, and it is known to like have better spatial and temporal accuracy in terms of mass loss signal. And the way which we get the signal is like it has a function and it has a statistical formula where we do basis function and we try to recover the signal in terms of eigenfunction. So we obtain like maximum information from the first 4 eigenvalues that you see here. Like alpha is the eigenvalues, and information that you get is from 90% up to like 50%, and this is shown for Gulf of Alaska North and Gulf of Alaska South. And because we have these user-defined functions, we are able to like isolate and see what's actually happening actually on a defined region. And once these signals have been recovered, we apply terrestrial water storage and then glacial isostatic adjustments to get the mass loss signal. And then moving on to my model, and as I mentioned, that there are several steps in the model, which is much similar to the glacier model intercomparison projects. And maybe we may not be better at this, but what we're trying to do is like understand the component, the GRACE component into our model, and how well we can do ablation and accumulation rates. So what happens is that we first use these tuning parameters, which I mentioned in the formula, where we have several parameters in ablation and accumulation, and we calculate the mass balance, which is basically sum of accumulation and ablation. And then in the model tuning step, we tune our model in such a way that the variance between the model and the GRACE is minimized. And then what we do in order to like project that we did for period between 2002 and 2019, and in order to like to project these modeled mass balance for future, we use the much simplified version of the volume area evolution scaling method to understand how the area and volume changes over time. And this, we use it along with the CMIF5 climate ensemble data to understand what's the future projection until 2100. So the model has several steps, which I'm trying to explain, which is probably like 5 steps of input, initialization, calibration, optimization, and future projection. And what you see here is the mass loss signal that we obtained from the GRACE solutions for Alaska, Baffin, and Ellesmere. And their corresponding mass loss curve from GRACE, and for which we have minus 36 gigatons from Alaska, which is Alaska, and then followed by which we have minus 7 gigatons of mass loss, and then for Baffin, which is minus 26 gigatons. And then when we tune this model with sensitivity parameters, what we get is we have this mass loss curve from our model, which is somewhat almost similar to what we get from GRACE. And I'm not like shown one on top of the other because we want to see what's the sort of seasonality that we get from our model. And we find that we get good seasonality from our model, which is based on ERA5. And I'm also trying to test with how it works with ERA5, which is one of the most recent reanalysis product, and also with ERA interim. And also we find, like, there's not much seasonality thing which is going on in Baffin, and there's some seasonality with Ellesmere. And when we try to understand the sort of like our model performance, we sort of get a correlation of like from 88 to 93%. We're still like working on this at the moment. So we're still not like completed with the experiments. And then we find that the bias is also okay for the observation period that we are considering. And then the other thing that we are trying to do is how well models, because our model did not use direct observations in the calibration phase, we are trying to understand how we can extend this study and understand what's the contribution from glaciers, from individual glaciers, say benchmark glaciers in Alaska, Canadian archipelagos. And what we find is, like, we have very small number of glaciers for direct mass balance. So we are trying to understand how this could impact our model, like globally and also regional, which is one of the challenging things with the model. And also, even though there are several glaciers the WGMS that has records of direct mass balance, what we end up is like we just have like 5 glaciers at the moment, which has good records of mass balance between the time period that we are looking at, which is 2002 to 2016. So at the moment we're trying to like understand how our model performs at a glacier scale, to understand what's happening with these benchmark glaciers, because we know these glaciers are losing a lot of ice like rapidly. And based on the volume, based on the calibration and optimization step, we use ensemble data sets from CSM, large ensemble, and then HAD-GM and MRI for 3 different scenarios, basically, which is the low emission RCP 2.6, and the moderate emission scenario 4.5, and the high emission scenario, which is 8.5. And which basically takes the temperature and precipitation as an input, and then we project our model to understand the future mass loss rates and also the sea level estimates. And what we find is, like, we still find that Alaska will lose a greater amount of ice until 2100, and followed by Arctic Canada North, and then the Baffin, which is like around minus 57 to 85 gigatons. So at the moment, we are trying to understand like the uncertainties which is coming from our model, because the way in which we use these GRACE observations in the calibration. So we are trying to understand there are different sensitivities that could actually impact the future projections. So one is the input that we are trying to use, which is basically ERA5 or ERA interim, and then the model itself, and then the climate ensemble data sets that we are trying to use. And now we also have the CMF6 data set, and also the dynamics part, because we've used volume area scaling, and we're trying to understand how well our model performs. And again, maybe we may not be better at this, but what we're trying to do is like understand the contribution from GRACE in the glacier model, and also trying to understand if you have like the ways of representing the spatial patterns of mass loss from GRACE, and how this could actually impact our model. And lastly, the how well it can represent the WGMS benchmark glaciers. So this concludes my talk, and I'm happy to take up questions at the end of the presentation. And here are my information if you want to reach out to me with any suggestions. So I'm happy to take any suggestion, comments regarding this work. So thank you so much.
Wonderful. Thanks so much, Lavanya. I forgot to mention in the start that for these early career talks, we'll save all the questions for kind of a 15-minute time slot at the end of all our 3 speakers. So if you have questions for Lavanya, feel free to put them in the chat, or just keep them in your mind until our question time. So our next talk is by Julian Williams. Julian's a third-year PhD student in environmental engineering at the University of Texas in San Antonio. Julian's an international student from Jamaica and does outreach work, including teaching GIS, math, and physics. Julian's never ridden a bicycle. Oh, you're missing out. But has done stage performances for over 15 years. So now we'll hear from Julian on sea ice lead detection in the Arctic.
Hi, everyone. So thank you for the introduction. My talk today is going to be about lead detection in the Arctic Ocean in the offshore Alaska and Beaufort Sea area. So the first thing that we're going to talk about, so this is just one static screen here for you to follow along with me. So what are leads? Leads are fissures or cracks in the sea ice surface, and it follows very close to the same concept of plate tectonics, where you'll have plates that diverge, and in those cases you have those openings of the fissures in the ice surface, and that's where you have open water being exposed. So if you think about that, the importance of leads and why we want to be able to study them, to quantify them, and be able to map them is because primarily they are the major regulators of heat in the Arctic. So because of that, we want to be able to quantify them, see how they change, and look at them on a time series. We also want to be able to navigate. We want to be able to find the best pathways from one point to another across the sea ice surface in the event of a search and rescue situation, habitat monitoring, and different scenarios of that type. So for the project that we're undertaking here, the type of lead being an open water lead or a thin ice lead, as we're seeing here in the objectives to detect the lead type and their fractions, we want to be able to say where the leads are open water leads and where the leads are thin ice leads. And by extension, we will find out what areas are actually thick ice areas. So in this case, we're seeing places like this where you can have open water leads or thin ice leads. And from that, we also want to be able to validate these areas that we detect leads in SAR data. So the primary data set that we're using here is the Sentinel-1 synthetic aperture radar. And that is available during polar nighttime, since at that time we have heavy cloud cover and optical images will not be able to do that. But we can validate the classifications that we have with the Sentinel-2 data, which is a multispectral imager, which provides the optical images. So if you look at this plate here, on the right-hand side, we're seeing the SAR data, an example, the HH band, and the classification on top of that. And here we're seeing the MSI example of the same area, the bottom here, and the classification at the top. So we want to be able to validate the areas that we see, in the SAR on the optical image. So what we want to be able to do is to perform time series analysis with the lead geometries that are there. So we want to be able to quantify where the net orientation is, the changes in the lead width, length, and the distribution, because that over time will give us an estimate of the energy that is available in the Arctic and that's being dissipated in those areas. So the study area that we're looking at is in the Beaufort Sea region, right off the coast in Alaska. And that's buffered by these geometries here, the hard coastal areas. And that I think also has to do with the orientation, especially of the leads, and we'll talk about that a little bit later. So in addition to the Sentinel-1 and Sentinel-2 data sets that I mentioned in terms of classification and validation, we also want to use the ISAT-2 data as well in terms of a laser altimeter that will be able to sequester areas and to separate areas that are both elongated regions, which are typically leads. But in the case where, if you think about, again, the plate tectonic scenario, where in some places you'll have divergence, in some other areas you'll have convergence, and in those areas you'll have ridges being formed. But they're both elongated features, and those features are not as distinguishable in the SAR as it would be in the MSI. So to do that, we want to be able to say what the average freeboard or what the height of the ice surface is in the image to separate elongated features that are leads as opposed to ridges. So that is a third data type that we like to use. So in terms of the methods, one of the very important parts of classifying with SAR data is to do major corrections. So if you think about SAR and synthetic aperture radar and how it acquires images, it always acquires at an oblique angle. Sentinel-1 in particular acquires images from the to the right. So for each subswath, which is a separate tile, so subtiles within the overall image or scene, there's 5 subswaths in the case of Sentinel-1, and at the edge of each subswath, you have a very high return. So that causes a source of error or something that will cause a misclassification of the ice surface in that case. So here we do apply an automated correction process so that the images that have that problem, especially the cross-polarized band, which is the HV band, we can remove that information or that error so that we can have a smoother and more accurate classification scheme. The Sentinel-2 is a little less brutal. Apart from just removing the general cloud cover, in some cases we'll have to subset the image just to remove any residual cloud areas, because the clouds can also be misclassified as thin ice areas. So we want to be able to move that as well. So in terms of this method, and you'll see here something called SVM, that is a support vector machine, and that is a method, a supervised machine learning method. And from that, we are able to sequester the areas that are by their lead types. So that is, our classification is very much centered around the image segmentation. So in the case of this cloud computation process that we employ here, it's called a SNCC, and it's an image segmentation process that we apply here as well as with the surface roughness. So in terms of surface roughness, that goes again as well to be able to sequester areas that are leads and are ridges. So if you think about ridges are high surface roughness areas, while the flat areas that would be lead areas, you would see that difference in surface roughness. So that is something as well that it incorporates in the machine learning technique and the subsequent classification. So in terms of the supervised machine learning that we employ here, we go for the support vector machine model because it just performs better. There are other methods that exist. They will perform up to 20% worse than the SVM. And from that, we actually are seeing a classification accuracy of around 91%, as it is at the moment. And again, we're using the freeboard to separate the ridge areas from especially the thin ice lead areas. So from that, when we're able to classify all of this information, we're able to do a vector analysis, because now we're not using a raster, we're not using raster data anymore. We've gotten the different classes, and now we're able to convert that to a vector analysis. And from that, we can sequester our lead fraction. So the lead fraction is the percentage of each type of lead or the ice type for the given total image tile. So here's an example of that. So we can see the different percentages from open water as opposed to thick ice, as well as thin ice areas. So this is what we're going for. And from this, we can be able to tell what the changes over time in the ice cover is like. Okay, so what we're seeing so far and what the general net orientation of the leads is towards the east into the Banks Island area and the Canadian archipelago. And that probably has a lot to do with the fact that these are hard geometries that the ice can drag against and open and close right against. And I will show you a website that we've created to track these things as well. So even though the supervised machine learning through the support vector machine does give a class accuracy of 91%, we want to do better than that. We want to be able to get to at least 98%. And we think we'll be able to do that with a convolution neural network. And that should also be done through a cloud computation platform as well. So that's what we're also going for. So if we switch over to something that is at the moment called Odin, this is a website being developed primarily for the purpose of navigation. And here we can see where the lead areas are. We can also track the daily weather based on wherever you are in that area. So there are different widgets that are supporting this effort here. So this is the type of thing that would be used in the sense of probably a search and rescue situation. That type of work actually exists in the European polar regions where there's an instrument called ISAR, and it's specifically for that purpose. So at the end of it, we'd also like to integrate this to be, again, a tracking type of situation. And if we just look at this figure here, where you're seeing the progression by days, I'm sorry, the dates aren't actually showing up, but it shows that closer to the geometries as I was saying before, if you look at some of the tiles that exist here, as it gets closer to the edges of the geometries, we're seeing an increased lead prevalence. So this is the type of tool that we like to be able to use to produce in terms of a website that is useful and open for the general public, especially indigenous people who may also go fishing in those areas for fisheries and so on. This is the type of tool that we'd like to develop and use our time series analysis to support those efforts. Thank you.
Awesome. Thanks so much, Julian. Great. And yeah, like before, if you have any questions, please throw them in the chat or hold on to them for our question session. So our final talk of today will be by Anna Bergstrom. Anna just started as an assistant professor in geosciences at Boise State. Is that right? I hope so. This January. More broadly, she's a watershed hydrologist and biogeochemist with a passion for working on and around glaciers. And so Anna will talk to us about the role of sediment on hydrological and biogeochemical connectivity on McMurdo Dry Valley Glaciers in Antarctica.
All right, thank you very much. Yeah, I just started as an assistant professor at Boise State University this January. So this work that I'm going to be sharing with you is primarily from my dissertation research that I conducted at the University of Colorado and just finished up last spring of 2020. So before I dive in, I just want to make a quick thanks to my mentors and collaborators on this work. So my PhD advisor was Dr. Mike Gusev, who's the lead PI of the McMurdo LTER, Kathy Welch, who's the project manager for the McMurdo LTER and the analytical chemist, Matt Cohen, who is a professor at University of Florida, an awesome biogeochemist who came down with us for a season to work on what you'll see in the second half of the talk, and then Joel Singley, who is a PhD student with Mike Gusev, who worked closely with me on all of this stuff. And of course, none of this could be done without extensive help in the field. So I had a number of people working with me, and then all of the contractors and field support staff who helped make work in Antarctica possible. I probably don't have to convince any of you, but we all know that glaciers are of critical importance to their landscapes. So they are a supply of water for downstream ecosystems. They help maintain ecosystem functions, things like maintaining stream temperatures, and they can be a supply of nutrients. So most melt is generated on glacier surfaces, and then it travels from there. So we can think of glacier surfaces as the true headwaters for both the glaciers and the downstream ecosystems. And so there we have this opportunity to set this initial chemistry of the meltwater. And a lot of work has really started appreciating how glacier surfaces can act as this zone of storage of water as well. So in firn or in in low density ice on glacier surfaces. We can store water on the order of hours to years. And while that water is being stored, we can do further work to transform and set that initial geochemical signature. So that leads to questions like how are glaciers connected to their watersheds and surrounding ecosystems? How are these critically important glacier surfaces changing, and what do these changes mean for the downstream ecosystem? So we took some of these questions and looked specifically at glaciers in the McMurdo Dry Valleys of Antarctica. And for those of you who aren't familiar with the McMurdo Dry Valleys, they are the largest ice-free area on the continent, and they are formed by the Transantarctic Mountains blocking the flow of the East Antarctic ice sheet towards the coast. And so we can see that there's these open rocky valleys, and particularly we're going to look at the Taylor Valley, which is the valley just above that McMurdo Dry Valleys label you can see in this image. So if we were to fly into the Taylor Valley, this is what the lower Taylor Valley looks like. You can see that we have these open rocky valleys and alpine glaciers flowing into and spreading out on the valley floors. And these are cold-based glaciers, which means that meltwater that's generated on the surface stays on the surface and drains off in superglacial channels. And so those superglacial streams flow off the glacier surfaces and feed proglacial streams, which then flow into these permanently ice-covered closed basin, most of the time they're closed basin lakes. And so those superglacial streams are a way to hydrologically connect our glaciers to our downstream ecosystems. And this is really important because in the McMurdo Dry Valleys, where there's water, there's the most productive communities. So this picture was taken just off the front of the Canada Glacier, which was the large glacier on the left-hand side of that previous image. And what we can see here, this black material that's kind of in the foreground is actually algal mat. So these algal mats need this consistent supply of water to maintain productivity throughout the summer season. So we can also think about how these glaciers are connected to their environment through aeolian connectivity. So in the McMurdo Dry Valleys, we get foehn wind events, which are these big wind events where wind speeds can reach over 20 meters per second. And those down valley winds can pick up material from the valley floor and loft it onto the glacier surfaces. So this picture was taken from the Commonwealth Glacier, which was the other large glacier on the right-hand side of the previous image. And that little piece of material in the foreground is actually a piece of algal mat that we saw a few images ago. So not only are we moving sediment and mineral material, we're also moving microbial material and organic matter along with it. And we can get it pretty far away from its initial source area. So lower down on the glacier, this is more typical for what it looks like. This is the taken on the lower half of the Canada Glacier. And what we can see is we have more concentrated and diffuse areas of sediment, both on ice surfaces and collecting in the bottoms of superglacial streams. So first, thinking about the ice itself, we know that diffuse sediment can be a source of solutes. So really quickly, conceptually running through what happens with sediment in the near ice surface, we get addition of sediment onto the ice surface. That sediment is darker than the surrounding ice, so it will absorb some amount of radiation, and it can start melting its way through the ice surface. Here in the McMurdo Dry Valleys, we do get some melt right on the glacier surfaces, but for the most part, the major zone of meltwater generation is just in the shallow subsurface, so the top 5 to 25 centimeters of ice. And so that sediment that's melted its way into the ice can interact with that meltwater that's being generated, and like I said, set that initial biogeochemical signature. And then as the season progresses, we can have this lowering of ice density. Some water is going to drain, possibly some sediment will move with it, and that sediment can continue to melt into the ice profile. So we wanted to compare this conceptual model to actual field data. So what we did was went out and collected hundreds of ice cores So at every single coring location, we collected cores in triplicate in a 2-meter triangle. We brought those cores back to McMurdo Station, sectioned them up into 5-centimeter sections from 0 to 25 centimeters, and then 25-centimeter sections from 25 centimeters to the end of the core. And all of our cores were, our maximum depth was 1 meter, because we were interested just in that top surface. And so we melted our core sections, we analyzed the meltwater for chemistry, and then we also measured sediment mass in each of those core sections. So first, I just want to talk about those seasonal sediment profiles. So this is an average of 3 cores taken early on in the melt season on the lower Hughes Glacier, which is a glacier a little bit higher up in the Taylor Valley. And what we can see is we have some amount of sediment in the top 10 centimeters, but we increase to a peak sediment concentration from 20 to 25 centimeters. And then below that, we really have little to no sediment. As we move through the melt season, correcting for ice mass or ice loss off the surface, what we can see is our sediment is condensing and moving deeper in our ice profile. And we're also getting slightly higher concentrations at depth below 25 centimeters. So when we compare this to our chemistry, first looking at chloride, which is a marine aerosol and is not necessarily linked to sediment, our chloride profiles don't look anything like our sediment profiles, which is not that surprising. And that's further reinforced when we look at a scatter plot of sediment concentration on the x-axis, chloride concentration on the y-axis. There's no relationship between sediment and chloride. However, when we move through and start looking at calcium, which is a weathering product, first thing is over time, over the course of the melt season, our calcium is increasing in concentration from early to late season across the profile. The second thing, when we compare sediment concentration to calcium concentration, we have a significant relationship between the two in our first set of cores taken early before we have any melt. But then once we start generating melt, that relationship breaks down. So that suggests to us that there's possibly some differential transport between what's going on with the sediment and what's going on with the dissolved solutes in the calcium. Zooming out, when we compare calcium to sediment in cores taken from glaciers and across the entire valley, we can see that that relationship generally holds. So I was showing you previously data from the Hughes Glacier, which are those 2 yellow points on the glacier highest up the valley, but we also took cores on 4 other glaciers in the Taylor Valley. So what we can see when we compare sediment concentration just across all of those cores to calcium concentration from those cores, that while we don't have a statistically significant relationship, generally in order to have high calcium concentrations, you need high sediment concentrations. But you don't necessarily get high calcium concentration if you have a high sediment concentration. The other thing is I should also note that these data now we're just lumping the top 25 centimeters of ice. And what we can see is our highest calcium concentrations are occurring in those top 25 centimeters, which also corresponds to the zone of meltwater generation. So just wrapping up this section, we know that sediment condenses and moves lower in the ice over the course of a melt season, and there's a loose association between sediment and weathering products, and there's potentially differential transport in the shallow ice surface over the course of that melt season. So that initial biogeochemical signature is set in the ice matrix where meltwater is being generated, but further processing can occur during transport between where that meltwater is generated and when it leaves the actual glacier. And so the superglacial streams are connecting that ice to the off-glacier system, and that's where we're going to look for that additional processing. So switching now to nutrients, some previous work led by Sarah Fortner hypothesized that there was nitrogen uptake in superglacial streams. And so that was hypothesized by a series of grab samples but they didn't actually test the uptake hypothesis. So that's what we went to do. And to do that, we had used a series of tracer experiments to measure nutrient uptake. So we adapted a method that's typically used in small headwater watersheds off glaciers and brought it onto the glacier surfaces. And so what that experiment entails is you have a conservative tracer. So we used sodium chloride, which should not react with anything. And then we have our nutrient tracer. So those are our, in this case, we were looking at nitrogen. And so you inject both of those tracers at the top of your study reach. You allow it to mix with that stream water and move downstream. And then you take a series of samples over time at the base of your study reach. And you look at the ratio between your conservative tracer and reactive tracer to see how that changes over time and see how you might have some uptake of your reactive tracer. So we conducted these tracer experiments on 3 different reaches on the lower Canada Glacier, but I'm just going to show you results from an experiment we conducted on the lowest reach with those blue points there. And I'm just going to show you results from our nitrogen tracer, although we did do a combination with phosphorus as well. So we were really excited that this experiment worked and that it followed expected behavior, because this is a whole new type of experiment and a new system. So what we can see here, this is over the course of our experiment. We put in our tracers, and then at the base of our stream reach, our concentrations increase to a peak, and then they decrease again as stream water moves through and we get back to our background concentrations. And so we can compare the ratios of, once again, our conservative and our reactive tracer. And what we can see is if we have points that are below the ratios that we initially put into our stream, we have nutrient uptake. And if we have points that are above that ratio that we initially put in, we have net release. So over the course of this particular experiment, we had both net uptake and net release, but the majority of points are below what we initially put in, so we had net uptake over the course of this experiment. So we can integrate through time and come up with a integrated uptake rate. So our nitrogen uptake rate for that experiment was 25 micrograms of nitrogen per meter squared per minute. So if any of you are familiar with nutrient uptake rates, you'll know that those are incredibly low. But given the system that we're working in, very cold temperatures, very advective streams, and not a lot of substrate in those streams, we were excited that we were able to measure this and actually show that there is nitrogen uptake in these superglacial streams. And so also, just really quickly, when we added phosphorus or phosphorus alone in our tracer experiments, we saw some interesting results, and that suggests linked physical and biological processes occurring in these streams. So to wrap it all up, sediment and biota associated with that sediment can influence the biogeochemical signature of meltwater. So the sediment itself is a source of weathering products, and the biota that's associated with that sediment can quickly modulate and transform nutrients as that water is being moved off the glacier. And so this sediment is really integral to connectivity between glaciers and their surrounding environment. So sediment itself can change the albedo of the system, and the sediment can then move in the ice profile and can also affect meltwater generation. The distribution of that sediment is going to affect where meltwater is being generated, and the amount and actual signature that's being created in the meltwater. And then the biota, once again, living in that sediment can be a nutrient sink. So we can think as aeolian and hydrologic connectivity as linked in this environment, and I suspect that's true in other environments, and sediment is the link between the aeolian and hydrologic connectivity. So just wanted to say thank you, and I think now we're going to move into the question period, and my contact information is right there. And then really quickly to make a plug for next week's talk. If you enjoyed this glacier biogeochemistry, you'll probably enjoy next week's talk. We're going to hear more, particularly from John Hawkins, Mark Skidmore, and Martin Trainter.
Wonderful. Thanks, Anna. If you all want to join me and thank all three of our speakers, Lavanya, Julian, and Anna, for their 3 great talks. Thanks so much, you all. And yeah, now we'll open the floor to questions. So feel free to, I think it's been easiest to put questions in the chat, but also if it's quiet, feel free to unmute yourself and throw your question out there to any of our 3 speakers. We're getting lots of applause, so that's great. Perfect. Thanks for checking Facebook, Tavi. So we've got one on Facebook from Adam. Adam, are you here? If you want to unmute yourself and ask it. Not online. For Anna. Oh, just very good presentation. Thanks, Adam. Oh, good, perfect. A question. Yeah, Roger, if you'd like to unmute yourself, go ahead.
Yes, thank you, Lauren, and thanks to all of our speakers. A quick question for Anna. Apologies if it's a bit too sort of physics rather than chemistry, but I enjoyed the presentation. This physical model you have of the grains, of the sediment grains falling down through the ice, do you see a vertical change in the grain size distribution? Because I would imagine the smaller grains lose their warmth quicker and get suspended, and the bigger grains stay warmer for longer and drop down further? Or is that an extremely naive view from a seismologist who once again has wandered into the wrong room?
Yeah,
but is enjoying it?
Thank you. Yeah, that's a good question. And so I didn't show any modeling results, but I took an energy balance model that's been used for the McMurdo Dry Valleys previously and added in a sediment transport component. So it's really primitive right now, but I would suspect the processes that you were referring to are actually occurring in the ice profile. And that is something that we need to look at by looking at grain size distribution from our field data and sort of coupling that into our modeling work, but we haven't gotten to that yet. But I think what you've touched on, yeah, is likely to be happening.
That's cool. Thanks very much. Look forward to hearing the next chapter.
Yeah.
Wonderful. Now another question for Anna from Paco. Paco, if you want to unmute yourself, go ahead. It looks like you're still typing, maybe.
Yeah, hello. Thanks for all presentations. Yeah, I was just curious about whether you have done similar studies in other regions or other glacier regions, and if so, if you have found any significant difference. And if not, maybe in what glacier region would you expect similar environmental conditions as those that you find in the dry valleys?
Yeah, so to clarify really quick before I start going off on tangents, are you thinking of the nutrient uptake side of things or more of the sediment dynamics side of things?
Sediment dynamics.
Okay, yeah, so I have not done studies anywhere else. I've been primarily focused on glaciers in the dry valleys. I think based on reading, what I would expect is this would be true in places where you have energy balance dynamics dominated by solar radiation, rather than fairly low melt environments. Otherwise, you get to the point where you just have a bunch of surface melt and that sediment is being washed on the surface before it has a chance to melt in. And then on top of that, you need kind of the right sediment concentration. So if you have too much sediment, we all know that you can end up kind of creating like a bit of a shading effect, rather than those individual grains able to melt down more diffusively. So that's what I'd expect, is kind of that combination of energy balance dynamics and sediment distribution that would lead to similar conditions. So I can imagine places up in the Arctic where you might see similar dynamics. But like I said, I haven't actually had the fortune to do this elsewhere.
Okay, thank you.
Great. Thanks, Paco. Roger, did you have a question for Lavanya? Did you want to ask that?
Yes, thanks very much. I've got one for each of our three speakers. So Lavanya, thank you as well. I mean, GRACE is an experiment whose capacities have excited all of us, and certainly our students. Just a very general thought, is it particularly good in the polar regions in terms of its coverage and its capabilities and so on, as opposed to anywhere a bit further, lower latitudes and so on?
Yeah, the problem with the lower latitudes is that there's a much noise which is coming for a smaller region, if you take like a smaller regions, but I think it works pretty well for like the Arctic region, because we tested for the Arctic glaciers, but also been testing it for Scandinavian regions, say Iceland. So it seemed to be working really well, but there's also the uncertainty component that's coming up from these smaller regions is quite large compared to the polar regions. So that's something that we need to bear in mind, but we do get the good seasonality from these smaller regions. So it's just a compromise between like the temporal resolution and also the seasonality that's coming from these small, especially small regions.
Well, I'm sure if you ask the whole of Iceland nicely, they'll organise themselves in one big place with a load of rocks, and you can test it against a measured mass change. they're a fun country. Thanks very much. Cheers.
Yeah, thanks.
Wonderful. Ellie, do you want to unmute yourself and ask your question for Julian?
Sure. Yeah, so I was, great talk. That was really interesting to see how you're using image classification to get at how the ice leads are changing. I was wondering, so you mentioned that one of the goals is to do time series analysis of the ice leads, and I was trying to imagine like what aspects of the ice leads. Are you looking at like the different classes of the leads, or are you particularly interested in certain features of the leads?
Thanks for the question. So we're really interested in looking at the different parameters of the leads themselves, so by each type. So we want to know, for example, the change in the length of the leads over time, the width of the leads, because depending on the dimensions, we can give an estimate of what type of energy exchange is being available to the boundary cloud formation in the polar.
Great, thanks.
No problem, thank you.
Are there any more questions for any of our three speakers? Yeah, Roger, would you like to ask your question?
Thanks very much. I can get the complete set. Julian, thanks very much. That very topical as well with what we've just heard about how our A74, if that's what it's going to be called, has broken off in the Antarctic. To take the plate tectonics analogy a tad further, do you see any capacity to measure what the plate tectonics people call strike slip, where things are broadly moving past each other and they might open up little lozenge shape leads rather than a long linear one? Thanks.
Thank you for the question as well. That's also one of the stringencies of the classification scheme, being able to largely just define the geometry of a lead, because of course some might be a little bit wider than they are long, and they wouldn't necessarily geometrically classify as a elongated feature. They may be a little bit distorted in that sense. But yes, it should, in terms of using something like a convolution neural network that will, it will be able to identify things in terms of computer vision rather than trying to use a stringent mathematical definition of what a lead is. So that is the purpose of using something like the convolution neural network that will be able to have the computer learn what it should look like. So any of the small discrepancies and variations in what an elongated feature should be like could also be incorporated in what is classified as a lead. So that, yeah, that is also something that we think should be improved in terms of being able to extract any object that should be lead-like or elongated.
That's cool. Thanks very much.
Thank you.
Great, thanks. We've got just a few minutes left. Are there any final questions for any of our speakers? Neat. So maybe if you'd like to join me and kind of, again, just thank all of our three speakers. Nice work. Thanks so much, everyone. Neat. And Anna threw up a reminder for next week's seminar, again, related to biogeochemical research. So please come back and join us for that next week. Thanks for joining this week, and thanks to our speakers.
Yes, thank you very much to all our speakers. And next week's seminar is by special request to come and get some biochemistry. It was asked for, so at least one person should be coming, hopefully. See you all next week, and thank you so much, all speakers, and Lauren too.